Today in this video, we are going to talk about Chapter 13, Queuing Analysis. Queuing analysis is important because we spend so much time waiting in line, either physically or on the phone. And so it's important to be able to understand queuing if you are looking at customer service. Queuing analysis is going to use probability, and we'll see that as we go through the chapter. Most operations have enough servers that they can handle customers in the long run. But, as you know, customers don't arrive at a constant rate, and they're not served in an equal amount of time, so these waiting lines can increase and decrease as time goes forward. So we're going to use an approach that looks at average customer arrivals and average service time. In this video, I am going to focus on definitions. I will show you a sample of the formulas, but we'll talk more about the formulas in class. Our first definition is called queue discipline. This is the order in which the customers are served. Usually, customers are served on a first-come, first-served basis. You can probably think of some examples where that's not true, but generally this is how it works. And in this class, we are going to focus on the first-come, first-served queue discipline. The calling population is the source of customers, and it can be either infinite or finite. In this class, we are going to focus on what's called an infinite calling population. In theory, it's infinite, though of course there aren't an infinite number of people on the planet. Of course, you could have repeat customers, but still infinite seems a little big. But in theory, we'll have an infinite calling population. The arrival rate is the frequency at which customers arrive at the waiting line. Usually this is given as so many customers per minute or so many customers per hour. We are going to assume that this is a Poisson distribution. If you haven't had statistics yet and you don't know what that means, don't worry about it. It's not critical to understand this distribution to be able to do the work in Chapter 13. If you do understand this distribution, you will see where some of the formulas come from. And the notation for the arrival rate is lambda, the Greek letter. The service rate is the average number of customers served in a time period, and the notation for that is the Greek letter mu. We're going to start by looking at single server models. Here's a diagram of what those look like. To me, this looks like a grocery store. We could have one server available and people waiting in line, or they could have more than one line open, but everybody in that line is waiting for that single server. The assumptions of the basic single server model are that we have a first-come, first-served queue discipline with an infinite calling population. We assume that the customers arrive according to a Poisson distribution. Usually we assume that the service times follow an exponential distribution, but that's not necessarily set in stone. Keep in mind that customers must be served faster than they arrive, or we build up an infinitely large queue. Some of you have maybe been on hold places. I know I have, where I'm pretty sure they don't have enough customer service representatives, or I wouldn't have been on hold for so long. So just keep in mind that we do need to serve customers faster than they arrive. As I mentioned before, I want to focus on definitions in this video, but here's just a sample of some of the formulas. So the formula is not difficult. Once we know the average arrival rate for the customers, the average service rate, we can use those to compute some other averages, such as the number of people that are actually in the system, the number of people who are either waiting or currently being served. We also have some formulas for some different probabilities. This is an example of a formula called the Utilization Factor, and this is the probability that the server is busy. There are lots of other formulas in this chapter, and I'm not going to go through them all now. We will look at the formulas more in class. We will also look at formulas for situations where the service time is undefined, meaning that it's not necessarily an exponentially distributed service time. We will also, in class, look at multiple server models. To me, this looks like the post office, the difference between the post office and a grocery store. At my post office, we all wait in one line, and there's usually 2 or 3 people there to help us. And whoever finishes, then the first person in line gets to go to that server. So we also have formulas for this situation. 3 more definitions before I finish up this video. Some other items that contribute to queuing systems are systems in which customers balk from entering the system. So they see the length of the line and they decide, I'm not even going to get in line. And I know I've done this. I expect you have too. Or they're in line, but the line's not moving fast enough, so they just leave. And we call that a renege. Another definition is jockeying, where you move between the lines. You think the other line is moving faster, so you switch. And of course, as soon as you do that, then the line you were in before starts moving. That's called jockeying. In summary, queuing analysis is important because we do spend so much time in lines. In class, we'll cover the formulas for both the single server and multiple server models. We'll practice computing arrival rates and service rates. Thanks.